just basically like homework problems. Just we have to
Yeah,
show you the work.
it'll be of the I mean, obviously not the same problems, but I just randomly pick homework problems and then change them
Hmm.
around. So it's not
Okay,
it's yeah,
it's not like definition or anything. Okay, cool.
no, it's not like multiple choice definitions or anything.
Okay,
Uh
thank you.
the exam somebody posted it's chapters 5, 6, 7, and 8. So it was Jordan who right. So it's from the beginning of the semester up through and including the chapter on capacitors, which is 8. Okay, other things where we start? All right. So yeah, so we left off and there's an example on the I did a longer example on a video that I posted last night. So the last thing last couple things to talk about with capacitors is one, so if I have a capacitor wired to some battery, and this has voltage V, we know that this thing will gain charge, plus charge here and minus charge here, until the voltage across it matches the voltage source, right? And then how much charge is it going to take to get V volts across? Well, that's what the capacitance tells you. How many coulombs it takes of charge on these plates to get V volts across it, and that ratio is the capacitance. Okay, so once you've done that, and then let's say we disconnect this and we just take these two plates here, we know that this thing stores energy. It has some energy stored in it because I could connect this to something else and discharge it through like a light bulb or whatever I want, or through someone's finger, whatever. And the energy would be deposited as the current flowed. And we'll talk about how you extract energy out of current flow and voltage difference in the next chapter. Probably a little later today, we'll actually get to that. But let's just think about for a second how much energy is actually stored in this capacitor. Well, I mean, there's a lot of ways to derive this, but one of the simplest is just to imagine that we had two neutral plates and we were going to pick charge up. And let's just say, I know in reality you move electrons, not positive charges, but moving an electron this way is the same as moving a lack of electron that way. So it's the equivalent of, if you take a bottle of soda and you shake it and you tip it this way while the cap is on, you see bubbles rising that way, and you see bubbles rising this way is the same as soda moving that way, right? It's just lack of soda moves up. And so you say a bubble moves up. So we can think of this as being positive charges being gradually moved a little bit at a time from this plate to that plate. And from that, we'll be able to figure out how much total work does it take to move all of the charges to get plus up here, total charge, and total minus charge down there. So let's do that in steps, and you'll see why we have to do that in steps. We're going to say the work needed to move all of the plus charges up here, and then when you do that, then you leave negative charge left over down here. Or if you want, you move electrons this way and you leave lack of electrons up here. So it's going to take some work to move each little bit of charge. Well, how much work does it take to move? Let's say we start, this thing is partly charged, let's say, and now I take another plus charge from here and I move it this way. How much work does it take to do that? To move this one little element, this one little bit of the total charge that we moved? Well, that's going to be equal to the voltage that's currently on the voltage difference across here, right? If there are 5 volts across here and I move 1 coulomb of charge, it takes 5 joules to move it, right? Because voltage is joules per coulomb. All right, so what does this mean? What this says is by writing it this way, that's not V times Q, that's V of Q. That's saying that, look, as I'm moving charges, each time I move a charge, there's a certain amount of voltage on this thing. And so the work it takes to move this little element of charge dq from this side to that side is equal to whatever the voltage difference is right now that this charge sees times its own charge. So it's V of Q joules per coulomb times dQ, coulombs. So the basic idea, so we'll finish this derivation, but the basic idea is that you can't just say, I mean, what you'd want to say, if this were really simple, you'd say, look, it's V volts across it. So this is wrong, what I'm going to show you, but I want you to see why it's wrong. So you could say, well, look, there's V volts across this capacitor, and I'm going to put plus charge, plus Q up here, and minus Q down here. And so how much energy is stored in there? Well, you would think, well, if there's 5 volts across the capacitor, and it's charged to plus 1 coulomb there, minus 1 coulomb there, well, then it must be 5 joules. So you would think that the energy, if you did it really quickly without stopping to think about it, you would think the energy, your book often uses U so that it doesn't get mixed up with E for electric field. You would think that the energy was just Q times V, the total charge on the capacitor times the voltage difference across it. That sort of makes sense. So that sort of makes sense. The reason this is wrong is because if you start with a neutral capacitor, this first bit of charge that you move, this little, so it's uncharged at this point. So this little element of charge dQ that I move from here to here, it doesn't take, the first one, it really takes me no work at all because there's no other charge moved yet. And so there's no electric field pointing downward against the motion of this charge. There's no potential difference. And so this one kind of goes for free. So now I have a tiny bit of positive charge on this thing. And so there's a very weak electric field pointing downward. So this next element of charge that I move, that is going to take a little bit more work to do, a little more energy, because now it's moving against a weak electric field. And you get the idea, as I move more and more charge, each time I move charge, the field gets stronger. And so the next element of charge I move is going to take more work to do. So that's the origin of this. We're saying dw, integral of dw, we're summing the work needed for each little charge element. And we're saying a particular charge element that's going to move, it's going to take the volt, it's going to cost the charge of the little element that I'm going to move times the voltage that it sees at the time it moves. And that voltage that it sees depends on how much charge has already been moved. The voltage on this, across this capacitor at the time you've already moved charge Q. Okay, but you know that voltage as a function of Q is just Q over C. The voltage across the capacitor is the charge on it divided by the capacitance, right? So all I'm doing is writing V of Q, the function voltage as a function of Q is just Q over C times dQ. And I need to integrate that from Q equals 0, the starting point when I start with a capacitor that's neutral. I haven't moved any charge, and I need to keep moving charges until I have moved a total charge of capital Q. That'll be the final charge. Plus Q up here and minus Q down there. So now what is the total amount of work that it takes to move all capital Q of the charge? Well, this is not a very hard integral to do, right? You know, this is 1, so that gives you Q squared over 2. So that's equal to Q squared over 2C, right? So you get 1/2 Q squared, plugging capital Q and 0. So you get Q squared over 2C. You can also write that as 1/2 CV squared, right? Because you know that Q is equal to C times V. So I can rewrite this as C squared times V squared and cancel 1C. So you'll see it both ways. You'll see it as either Q squared over 2C or a half Q squared over C, or a half CV squared. All right. How to get the ASA? So how to get the Q over C? Well, if I tell you I already have moved some charge, and the current, at this instant, the amount of charge here, I have plus Q here and minus Q here. What's the voltage across this thing? Well, the voltage across a capacitor is always the charge on it divided by its capacitance. So at this moment, there's plus Q and minus Q, and so the voltage on it is the charge that's on it over C. Is that okay, Asa?
I have a
Asa
quick
has gone
question.
dark. Sorry, go ahead.
So, when we evaluate the integral, so it says small q equals large Q on the top of it?
Yeah, you're integrating from the little q represents how much charge have you moved so far.
Okay.
And capital Q is how much charge, how far are you going to go? What will be your final charge on this thing? So this is, you can think of this as a snapshot midway through.
Mm-hmm.
We're going to keep going until we get some final amount of charge, and let's label the final amount of charge to be capital Q.
All right. Thank you.
Okay. What else?
When you're setting large Q as your final state, are you adding large Q positive and large Q negative, or just one side?
Yeah, I mean, that's a funny thing just about the way we talk about capacitors. If you put a charge, Q on this one, plus Q, and a charge minus Q there, we say this capacitor has charge Q. I mean, yeah, technically, I guess it has plus Q and minus Q, which would be 0, but that's not very helpful. So when we say the amount of charge, we mean that amount positive on one side and negative on the other. So this means we're going to keep going until we get plus capital Q on one side, minus on the other.
The assumption is that the charges are equivalent on either side of the capacitor.
Yep, they'll always be equal. And in fact, in this instance, that they would have to be, because the way we're doing this, we say we start with neutral plates, and I move charge. Let's say I move electrons from here to here. So that means this one gradually becomes more positive and this one becomes negative, but I'm not changing the total amount of charge. So they would have to stay equal.
So is there a special integration that you have to do if they are not the same?
No, I mean, because you couldn't have that, because when you're talking about a capacitor, right, you talk about the capacitance of an object to store equal amounts of charge on how much equal amounts of charge would it store for a given amount of voltage across it. So if you put a voltage across two neutral plates, they will pick up an equal amount of charge.
I see.
Right? Because charge would be conserved, right? Your battery or your source was initially neutral and your plates are neutral. And so it's going to be, I mean, in principle, there's nothing to stop you from taking a plate and putting plus 5 Q here, or let's just say plus 5 coulombs there and minus 1 coulomb here. And you could ask what the electric field in here is. That's fine. Right? You do sigma over epsilon naught and sigma over epsilon naught, and you could do that. But that's not the same as saying what's the capacitance of these two plates, right? I guess the way to think of it is, remember that capacitance is a function of geometry. For two parallel plates, so if you have two parallel plates and each one has a surface area of A, the capacitance of this, and they're a distance d apart. the capacitance of this object is epsilon naught A over D, which we derived a while ago. So, right, it is only, you don't have to know anything about how much charge, or the equal charges, are they like, anything else, what's the voltage. This is just a number that depends on how big these plates are, how far apart they are, and a constant of nature. And so, sorry, I was looking at the chat question, but I think Dan answered it. So this is just a function of the geometry itself. So there's no talk about equal or unequal. This tells you just how much charge would come onto those plates for every volt I put across them. Does that sort of answer what you're asking, Connor?
I think so.
Okay. And Jeffrey, does your question make sense? Does Dan's answer make sense? Where did Q squared come from? Jeffrey has also fallen silent. I love Zoom. It's like never-ending joy. Yeah. So Jeffrey, right. So here you're integrating Q dq, so you get 1/2 Q squared, and then you got to plug in capital Q and 0. So that gives you Q squared. Technically, I guess we'd have a -0 here. Okay, so other questions so far? Okay. So we're going to do one more. This is a very qualitative thing. I mean, you can do it quantitatively, but we're not really going to do that. I want you to just imagine a simple case where I take parallel plates and I put plus charge on this one. So we have a capacitor, and let's say it's charged. Right? I put this thing across some voltage V, and this side develops a positive charge, this side a negative charge, and we know that there's a voltage difference V between them, because this is all one piece of metal, so it's going to keep building charge until it gets V. And how much charge it's going to take to get to V potential difference depends on the size and shape of the object. Now I want you to imagine something. So suppose I did that, and it charged, and it's all settled. It has, the total charge on this will be whatever its capacitance is times this voltage. And now I take and I put an insulator between it, just in the gap between them. So I put an insulator. And so I just put a piece of plastic between them. So, or I don't know, I put a cube full of, maybe I put a block of ice between them. What you know is that materials, right? Most materials are what's called polarizable, right? They all have the individual molecules have dipole moments to them. And so what's going to happen is I have an electric field that runs this way. Well, if I have an electric field that runs that way, that's going to align the molecules in this thing. And this is a little cartoonish, I'm sorry, but right. So quantum mechanically, if you have an atom, well, even that's cartoonish, right? But you have a nucleus, and then you have a positive nucleus, and then you have an electron quantum mechanical cloud. So the electrons have probabilities of being found at different places. If you apply an electric field to this thing that points that way, in general, the electrons will spend more time on this side. It'll change the wave functions so that this side becomes effectively more negative and this side becomes more positive. And then in our cartoonish way of doing that, we draw these little, and I'm sure you've seen this from chemistry, we draw these little ovals and we say, okay, this side now becomes positive, that side is negative. Now before this, if this field weren't here, they're just aligned in all random directions. But because you have an electric field pointing this way, these things line up to some extent, depending on the material, will tell you how much they line up. And so you'll wind up with basically an effective leftover positive charge at this surface and a negative leftover charge at this surface. Now, this charge does not match the density of that charge, but there is some. This has developed some effective positive charge down there and negative charge there. So what you can think of is this insulator is now running its own electric field that goes that way. Because this side's positive, that side's negative effectively. And so it runs its own electric field that points up. So what does that mean? Well, if that happened, now the electric field, if you're standing at this spot in space, is weaker than it was before, because you feel the electric field from the original charges you put there that are there and there, plus an electric field that points the opposite way. So this reduces the E field. And how much it reduces the E field depends on what's called the dielectric constant. E goes to E over, and your book is using K for this, E over K. So this material has some dielectric constant K. All right, so here's where this part you'll have to probably pause on your own later to think about. If the electric field gets dropped by a factor of K, it's now, if you're here, you say, oh, it's a factor of K weaker than it was, then the potential difference between these two plates goes down by a factor of K. So V goes to V over K. Patrick, you have a question?
Yes. So why did we label like the distance that isolator takes as a V?
Why did we label what?
Like the distance, like the length of the
Oh, I'm
isolator.
sorry. Yeah, yes, thank you. That's a good point. What I'm saying, this is not, in this case, is not labeling distance. These, if it's, I don't even know what shape this object is. Maybe it's concentric cylinders, maybe it's concentric spheres. This is just saying that there is V volts of potential difference between them. Right? Physically, this could be, this is in a circuit. We always represent a capacitor as parallel plates, but it doesn't have to be. It could be a little sphere with, inside a larger sphere and two wires that come out, and you could wire this to some voltage V. And we would still, so this would be physically what the device looked like, but in a circuit, we would still write it this way. So the short answer to your question is this V, in this case, that's not representing the distance between parallel plates. It's representing the voltage difference between them. Does that make sense, Patrick?
Yes. So it's basically just a voltage difference between them.
Yes, yeah, it's just the voltage difference between them. So if the voltage goes down by a factor of K, right? So C is Q over V. If the voltage, when I slip this piece of plastic or whatever it is in there, the voltage dropped by a factor of K. Now I'm going to need to increase the amount of charge in order to, well, you can see what happens. So if V goes to V over K, C equals Q over V, and then V goes to V over K, sorry, V over K, then C goes to K, that's supposed to be a K, times Q over V. So and this was the original capacitance. So C goes to K times C. So the capacitance goes up by a factor of K. And this arithmetic is fine, but I think it's better just in this case to just think of why that makes sense. If I cut the electric field by a factor of K, so now it's weaker. I don't know, maybe K is 2. So now the electric field, let's say K is 2, the electric field in here is half as strong as it was. So now the potential difference, if these were parallel plates, the potential difference is just going to be the electric field times the distance I move from one plate to the other. But now the E field is half the strength, so the potential will be half as big, the potential difference. So now I've got to put twice as much charge on this thing to get the same electric field I would have gotten. So if I have to put twice as much charge on to get a voltage V, that means this thing is going to store twice as much charge as it did before you put before you put this slab of insulator in the middle. So the capacitance goes up by this factor of K, and this factor of K. So yeah, Allison, this is a constant, not a constant of nature, but a constant of the material, right? Water and plastic and different kinds of
So
plastics all have
it's
different
not the
values.
same K that we use in the Coulomb's law. That's
No.
a different one.
No,
Okay.
right. This is not K. Thank you. That's a good point. This is not K from Coulomb's law. This is just K for dielectric constant, which depends on the material. Sometimes you'll see it written as epsilon sub R. Different, like if you're looking at things online for dielectrics, you'll often see it written as epsilon sub R. But it doesn't matter. Whatever it is, it's whatever label you use. It's the factor by which the E field gets cut down in here, which means now you need more charge to get the same potential difference. So no, it's unitless. Okay, so questions so far? Yeah, so Liam, how fast does charge flow, distribute, equalize? That's a very good question, but we're not there yet. We can't right now, and you're right, this is sort of unrealistic. We're just saying, look, as soon as I plug this in, instantly this thing becomes charged. It doesn't really happen that way. How long it takes depends, for those of you who know this, on the resistance of the wires. And so we're going to soon talk about circuits where we have a capacitor and then we actually include some resistance, and then that'll let us talk about how long it takes to charge this thing. What would really happen is if you have Q as a function of time on the capacitor, it would charge like this. It would be basically an exponential fall toward Q over C times V. So it would start uncharged and it would rise like this, and after a long time, it would approach C times V, the charge that we've been just assuming happens instantly. And how much time this is will depend on what the resistance of these wires are. And it can be very fast. I mean, it can be microseconds, or it can be seconds, depending on, how big the resistor is. Right? Okay, what else? Other questions so far?
So I'm sorry. I missed a bit of the context when that limit, as it approaches CV. When does this happen?
When you are, so again, I don't want to go too much into that now, but we're talking about, so let's suppose you have this voltage, this battery, and I have a switch and it's open. And I have my capacitor here. And then you start a stopwatch, and at the time I slam this switch closed and complete the circuit. And what we've been doing so far is saying, well, as soon as I close this circuit, everything here is at all the potential V. This thing has charge C times V, all done instantly. And so what Liam was asking is, well, wait, that can't just instantly be charged, and it's not. So what we're talking about here is basically a preview of what we're going to get to in maybe a week and a half maybe a week and a half we'll learn later that it actually doesn't go instantly from Q equals 0 to Q equals C times V. It ramps itself up to that value over time.
I get it. I'm with you now. Thank you.
Okay. All right. What else? All right. I'm a creature of habit, and everybody is now horizontal instead of vertical. All right, maybe I can do that. Oh, good. And there, wow, 2 people with their camera on, 2 out of 120. This is awesome.
My hair is just a mess. I'm sorry.
Well, you know, whatever. Your hair is a mess. I didn't shave. It's all COVID. Right? We're all going to have to adjust to not going to classes in pajamas eventually. Okay, so good. So let's move on from here. So that pretty much ends what we're going to do with capacitors. So the next thing, so chapter whatever it is, chapter next. I get confused between Survey and the public domain book. Current and resistance, which is chapter 9. Oh, in fact, I want to take a quick poll of people. All right. So, yeah, let's use, I only have a few polls. So don't answer yet since I haven't asked the question. So greater than, less than, or equal. I want to know if those of you only answer this if you kind of have been looking and reading both the open source textbook and the the whatever Halliday Resnick. Is the open source textbook better than, so greater than, less than, or about equal to the to Survey? Yes or no is not an option. So it's the open source, if answer greater than if you think the open source is better, answer less than if you think the open source is worse.
And just what should we
And
do
equal
we
if you
haven't
think,
been
yeah,
using
they're about the same.
either. We've been
Either
using
is better.
just one of
Yeah.
them.
And only obviously do this if you've had some experience with both. I'm just curious because I like the idea of saving saving students $150, but not if it's a worse textbook. Survey was very Saad, so you thought Survey was vague. So Saad, do you is the open source better? I mean, is that a reason why it's better? I assume you
Like
voted creative.
much more. Like it's much more clearer. Like in Survey, it was really vague when it explained the concepts, and then it asked questions that like you couldn't really refer it back to where they explained the concept to answer the question. But here it's a bit easier. But that's just me though. I don't know about the others.
Okay. Well, it looks like, I mean, it's kind of split. I mean, 8 people think the open source is better. Explanations open source, but Survey has problems that are much more relevant to what we're doing now. Okay. All right. So 8 people think the open source is better. 11 think Survey is better, and 17 think they're about equal. All right. Well. All right. Thank you. That's certainly not enough difference that, in future when I teach this class, I will go back to having students buy publisher textbooks. Okay. So before we, so we're going to talk about current and resistance. And I think probably of all the chapters we do, this is probably the easiest chapter we do. And it's a good time for it because I know you're studying for the exam. And there are certain points this is true in physics classes in general, there are certain points of time where it makes sense, in math classes, where it makes sense to pretend you are not in a class and just forget about all formulas and things and just write down what makes sense, right? So I'm going to ask you simple questions. Suppose I have water pipes and I have, let's say I have 3 gallons per second. You come and measure and there's 3 gallons per second flowing this way in the pipe right here. And then I have a junction here. So it's like a T and water can flow back and forth. So I have a pipe junction here. And I have, let's say 2 gallons per second flowing this way at this spot. So on your own paper, just write down the current and the direction in that pipe. Don't answer out loud. Just All right, what is it? Direction and an amount.
1 gallon per second up.
Yep. Why? What
Because-
formula did you use? Or did you not?
Hashtag brain.
Right, exactly. Right, you don't, I mean, yes, you can say, okay, the currents into a junction match the currents out of a junction, but I mean, come on, right? There's 3 gallons going there, 2 gallons over here. What do you think happened here?
I
Right?
used the formula 3 minus 2.
Right. It must have split off here. Then the 3 went to 2 that way, 1 that way. Right. Fair enough. If I changed it and I said, you know, you measured 3 gallons per second that way here, and then you measured 5 gallons per second this way here. Must be 8 gallons per second upwards here. Right? It's all got to go somewhere, right? So it must be like that. And yes, you can, instead of that, well, actually, before we do that, let's before I give you any sort of equation for this, let's look at another one. This one it's not really harder, but there's a, I don't know, it's you have to think for a second longer about this one. There's 8, you measure 8 gallons per second at this spot flowing that way, and you measure 5 gallons per second flowing this way at this spot. Label all the other legs. They'll flow in each of the other 5 legs. Direction and amount. And remember, right, you got to conserve water. So I don't know, this one ought to be 5 down. Because I don't know, if it's 5 gallons per second this way here, it better be 5 gallons per second downward there, or we're accumulating water somehow.
Then would it be safe to say it's 8 gallons per second up on the left side?
Yeah, sure. But it better be, because I don't know what else is going on, but it's 8 there, so it's got to be 8 here. Putting a curve in a pipe can't change the amount of flow. And so we must also then have 8 gallons per second here. We must have 5 gallons per second here. Now we got to think about this. Well, if you think that you got 8 coming here and then 5 going out, we must have 3 gallons per second going down. And then you better check that and see if that makes sense over here. You have 3 coming down and 5 coming that way, and sure, they meet to leave 8 going that way. Right? Yeah, so that's 3 gallons per second downward. All right. Okay, and I mean, right, this, when you talk about this with electric current in coulombs per second instead of gallons per second, right, it gets the name Kirchhoff's junction rule, but of course it's just common sense. If we change gallons per second to coulombs per second, the total charge or water flowing in to a junction has to match the flow out, and that's really all you've done here. So at this junction, the total inward flow is 8 gallons per second, and the total outward flow, 3 gallons per second plus 5 gallons per second. So if you didn't know this, if you didn't know that value and you just set it equal to some x, then sure, you would say the total flow in is 8 gallons per second. And the total flow out would be 5 gallons per second plus x gallons per second. And then you would solve for x and you say, oh, it's 3 pointing down. Now there's a little bit of subtlety to that. What if I did this, right? I say we have 8 here, forget the units for now. I have 5 here, maybe it's coulombs per second, maybe it's gallons per second. And let's just say, I don't know, I label it this way. And so I know if there's 5 this way here, there's 5 to the right there, another 5. And we've got 8 and 8. So let's just say I labeled it that way. Okay, so the total flow into this junction is going to be 8 gallons per second plus this unknown amount plus X gallons per second. That's the flow into this junction. The flow out is 5 gallons per second. So obviously, so X equals -3. So which is it? I mean, here we found that the flow was 3 gallons per second. Here we found it was -3. Somebody quick resolve that. Which is it? 3 or -3?
It would.
Both, yeah. Farhan, why? You got to unmute, right? Yeah, direction, right? So it is. It's -3 gallons per second up or +3 gallons per second down. So the sign is tied to the direction, right? Driving 50 miles an hour east is the same as driving -50 miles an hour west. And so it's identical. Okay, so this you'll learn as the junction rule, but yeah, of course, it's just makes sense. Right?
Professor.
Yes, scroll up.
Yeah, Ernst's plumbing theorem.
Yes, exactly. Dan, can you not see something? You say scroll up. I don't know if it's, I don't think it's, I can see my whole clipboard. You all right? You can unmute if you want to tell me what's going on.
I think
Oh,
that's
he
what
meant in
wanted you to
chat.
scroll up
Okay.
for. The
All right. Yeah, so it's a vector quantity. Right, so yes, we can rename Kirchhoff's law for me now. Okay, so that's a simple thing that we'll deal with, and we'll call it Kirchhoff's law when we get to it, but it's really nothing that you don't already know. And the units, we've already talked about this a little. The units for current are not gallons per second, obviously, they're just coulombs per second. So if I have a circuit like this, with a capacitor and a voltage, and when I close this switch, obviously, since this becomes positively charged and this becomes negatively charged, there has to be some current in this circuit. And that current gets the name of, usually we use I for the variable, like we use Q for charge, it doesn't matter. But it has units of coulombs per second. It's a sensible unit. You're asking how many coulombs, if I were to put a little scope here and look, how many coulombs pass over this point in the circuit per second? That is the current at that point. So be a little careful, right? When you ask about voltage, you don't ask about voltage at a point. Voltage is relative to something else. And so we may get sloppy and say, what's the voltage here? We always mean relative to 0 or relative to ground. But current, you talk about current at a point, not current difference. And it's coulombs per second, and it's used so much that gets its own name, which is amps. Okay. Okay. When we talk about current, there's 3 different velocities that come. So questions so far? Okay. So there's 3 different velocities that come up, and I like an analogy for this because otherwise it's tricky to think about. Well, it's not tricky to think about, it's just tricky to remember them. So when we talk about conduction, there are 3 velocities that appear or are relevant. The first velocity, and I'll explain these to you in a second, is the electron velocity. Yeah, all right, we'll do them in this order. And this is on the order of 10 to the 6th meters per second. A meter per second is about 2.5 miles an hour, so extraordinarily fast. And so this is about not a 1/3% the speed of light. So extraordinarily fast. Not an ordinary, no ordinary objects travel at 1 million meters per second. The second velocity that comes up is what's called the drift velocity.
I have a quick question. Does the electron velocity has like any letter, for example, like K or something?
Not like one consistent thing.
Okay.
No, not really. So the second velocity that matters to us is what's called the drift velocity. And this is on the order of 10 to the minus 4 meters per second. So the first thing you got to notice is this is incredibly slow, right? So that's that's a tenth of a millimeter per second, right? So it takes it 10 seconds to go, this far, 100 seconds to go a centimeter. That's a long time. So this is 10 orders of magnitude slower than that, whatever this one is. And so might as well at this point start to talk about these, right? So the electron velocity is, and this is, right, models of conduction is extremely complicated and it's fundamentally quantum mechanical, but we're going to, for now, do this little bit of a cartoonish model. If you imagine the free electrons, the valence electrons moving, the electron velocity is, if you take a snapshot of one of these, and I know you can't take a snapshot of an electron, but if you could, this is the speed. This thing is zigzagging around in all directions. And the speed that it is moving is 10 to the 6th meters per second. So on the order of 1% the speed of light. So extremely fast. The drift velocity is, it's zigzagging all back and forth, but in general, and here I'm assuming, let's say I put a voltage across this conductor, and now I got to be careful because we're using electrons. So this is the negative side, this is the positive side. So the electrons will gradually drift this way, right? So this thing is zigzagging around, but it is generally heading this way. And the speed that it is generally heading is this. So it's racing around back and forth, but it's extremely fast, but it's making very slow overall progress. Right. I liken these two to, if you go to the Adirondacks in May, as soon as you get out of your car, a cloud of black flies comes over to feed on you. There are two speeds. One, there's the speed of the individual black flies as they're zigzagging around in their cloud. And the second is the speed with which the cloud is gradually making progress to you. You don't need to be able to run faster than the black fly speed. You just need to be able to run faster than the cloud speed. And in fact, it doesn't matter. There is no point running because there's another cloud over there too. And so wherever you go, they'll get you. Yeah, Jeffrey, it is true. I've also heard my grad advisor had a great expression. He was a big Adirondack hiker. And he said, it is black flies that have saved the Adirondacks from development. Because it's a beautiful, wonderful place, but you don't want to be there year round.
A quick question, if I
Yep.
may.
About black
So
flies
just
or physics?
no, this is actually about the physics. So I'm
Okay.
just trying to write a definition for this. So could it be the speed at which electrons will drift towards a opposite charge?
I wouldn't say drift towards an opposite charge. I would say just drift in a particular direction, right? Let's say drift in the direction that they're being pushed by a voltage difference.
So drift in the direction that they are being pushed by a voltage.
Yeah, how about that?
Okay.
I like that one. Okay, so that's the drift velocity.
One
And
more
then-
question on that, real quick.
Yeah.
Is that drift velocity irrespective of the charge?
Irrespective of the charge. You mean its charge?
Or the charge difference between the two?
Oh yeah, like the voltage difference. No, the speed is this speed is affected somewhat, not this one so much. This is affected somewhat by the voltage that's across them, but it's not huge.
Okay.
And so the first thing you think when you look at this is you're like, wait a minute, 1/10 of a millimeter per second. how the hell do we ever get any light when you plug in a light? You plug a wire into an outlet, and it's, if the electrons are going to gradually make progress at 1/10 of a millimeter per second, it's going to be a long time after you plug in, right? So you have a voltage difference and you plug in some light bulb here. If that's the only progress that these electrons are making in the conductor, it's going to be a long time before your light turns on. You better start the day before. Right? So there's a third velocity. And this is called the current velocity. And this is about c, or 3 times 10 to the 8th meters per second. And you think, well, what other velocity is left? There's the rattling, there's the speed that they're rattling around, there's the speed that they're making progress. And then the third speed is the speed at which the news travels. I mean, I know this is all cartoonish because it's fundamentally quantum mechanical, right? When this electron moves this way, generally makes a little bit of progress this direction, that repels this electron. So that forces it to make a little progress that way, and so on through the wire. And that news travels extremely fast. That travels at basically the speed of light, just under. But in a real physical wire, it's a little under the speed of light, but not much. It's like 1 foot per nanosecond is the typical time in a real wire. Okay, so then the progress, and I like, in my analogy for this is that if you have a string of billiard balls all touching each other, and if I tap this one, the billiard ball is not moving very fast, right? I can give this a slow, kind of a gentle tap, and it kind of slowly moves. But the news, right? So they compress a little, but the wave of progress from one billiard ball, it doesn't take long for this one to move, even if it's far away, right? So that's the third velocity. As soon as I push on that one, this one moves slightly later, because when I push on this billiard ball, it squeezes a little, which then causes this one to squeeze a little. And so it does take time to propagate through, but not much, and much faster than the motion that I imparted to that billiard ball. Right. So this is kind of the speed that the news is traveling.
Wait, so is drift velocity 0 until there is a voltage, or is this always that?
Oh, excellent question. Yes, very good. I meant to say that. Thank you. Right. If there's no voltage, the drift velocity is 0. Very good. Right. So they're rattling around in random directions, but there's no bias for this electron to head that way or that way. So they're all just randomly going in any direction. Right, at this speed, and then this is 0, and this is 0 because there is no current. There's no net news to travel. Thank you. Yeah, thank you for picking that up. What else? Other questions so far? Okay. So we've sort of been talking around currents and what they flow in, but we haven't really actually gotten into it. So to do this, the first thing we have to talk about is resistance. And you have to, I want to use the word resist, you have to stop yourself from just thinking, right, there's a tendency to think, oh, resistance, yeah, I have Ohm's law, V equals IR, that's it. I don't know, there's some other stuff, but whatever, it's V equals IR. Don't do that if you actually want to know what's going on. It's not quite that simple. Yes, you can use this in a lot of problems, but there's a subtlety. This is not the definition of resistance. So what I want you to imagine is I take some voltage and I take an object, which we'll call a resistor, right? So I take an object, and a resistor is an object that opposes current flow. Right? And so this is one of those cases where you want to try to, if you just try to make up things, like decide how you want to define things, you'll almost always bump into either the standard definition, or you'll realize your definition has some flaw. And either way, it's a very good way to learn new concepts. It's probably the single technique I use more than anything else when there's something I'm trying to learn or don't understand. So, so a resistor opposes the flow of current, and some things oppose the flow of current more than other things, right? So how do you want to define how, so here I hand you this thing. How do you want to define how much resistance the object has? Well, we could just say resistance is not, let me make sure I'm using the notation in your book. Resistance measures the amount of voltage, or I would say, now let me change that. R is defined as the amount of voltage needed to drive 1 amp of current through the object. So if I have a piece of plastic, or, let's say I have a piece of plastic that has, it doesn't have infinite resistance. You can put current through plastic. So if I have a piece of plastic here, and then I have, so let's say this is plastic, and I have a piece of aluminum here, if I put a voltage difference across this, even a very, very tiny, this doesn't oppose flow of current through it. So even a very tiny voltage here will drive an amp of current through here, a coulomb per second. So let's say we get 1 amp of current going. So you would say this has a small resistance, because if I handed it to you and said, here, find the resistance of this thing, what you would need to do is put it, attach wires to it, put a voltage source that you can dial up or down, and measure, put what's called an ammeter here, and measure the amount of current flowing. And then you would put it up a tiny, tiny amount, and you would say, ooh, it was a tiny voltage I needed to push an amp of current through it. Whatever you got, maybe you got 10 to the minus 3 volts to get an amp of current. So you would then say this thing has a resistance of 10 to the minus 3, what's called ohms. This piece of plastic, you'd be cranking up this voltage quite high. You might need thousands of volts across this before you would get 1 amp of current through it. And that is the definition of resistance. The number of volts it takes to get per amp of current you want to go through it. So the resistance itself is defined, and this is where it gets tricky, because you look at this and you say, it's Ohm's law. Just multiply by I, it's Ohm's law. It's not Ohm's law. This is the definition of resistance, how much voltage it takes to drive a single amp of current through an object. So here is the question. Suppose I take some object. So questions so far? All right, if you're ever going to do anything in electronics or physics or anything, this is the moment to straighten out the difference between Ohm's law and the definition of resistance. Resistance defined as voltage needed to drive 1 amp through the object. All right, so fine. Let's say I take this object and let's suppose I dial this voltage up and up and up. And let's say I discover with my ammeter that when I drive 100 volt, put 100 volts of potential difference across this object, I get 1 amp of current flowing in the circuit. I would then say, therefore, this is a 100 this object has a resistance of 100 ohms. Okay. Are we ignoring what is scribbled? Yeah, Jeffrey, ignore that for now. I'm trying to show you the subtle difference between R being defined as V over I, and that is not the same thing as Ohm's law, which is V equals IR, even though it looks like you can just multiply it by I. So you took this object, you had to dial up the voltage to 100 volts before you saw an amp of current going through it. Okay, and so you then came back to me and said, okay, Jesse, that's a 100 ohm resistor you handed me. Good. Now I say, what are you going to do? I want you to take this back into the circuit, and I want 2 amps to go through it. What voltage are you going to set? Equals something, but I do want the same object. I want 2 amps to go through the circuit. How much voltage? Any ideas? 200 volts? That's a reasonable guess. Any other guesses? 101 volts? Yeah, could be. This is what Ohm's law says. So Liam, your guess of saying, I don't know, it took 100 volts to get, hopefully you weren't using that voice in your head, right? You took 100 volts to get 1 amp through this object. So probably 200 volts would push 2 amps through it. Sort of stands to reason. The harder you push, the more current you'll get through. What you just assumed, Liam, is what's called Ohm's law. Ohm's law assumes current is linear with voltage. And it's not always true. It might be that this particular object, if you put 100 volts across it, you got 1 amp, and therefore it's a 100 ohm resistor. But if you put 200 volts across it, yeah, you might get 2 amps through, but you might not. It might be off a little. If it is perfect, then we say the material is perfectly ohmic. But it is not the case that if you put 10,000 volts across it, that you'll get 100 amps through it. It doesn't work indefinitely over any range. And if you put 0.1 volts across it, that you'll get 0.001 amps through it. That assumption is what you are assuming when you say a material is ohmic. So V equals IR is what you say if the material is ohmic. And lots of materials follow Ohm's law over certain ranges of voltage, but you put too much voltage on them, the whole thing just melts, or it stops being linear after a while. So don't mix up Ohm's law, which is often right, and we'll mostly use cases where this is true. Keep that straight in your head, though, as not being the definition of resistance, okay? Okay, there are a lot of people who know a lot of circuit theory who still, screw up that volt resistance is not the same thing as Ohm's law. Okay.
So, how practical is Ohm's law and when applied to practical situations? Then, if it's not,
it's very useful, because a huge range of ordinary materials do are ohmic over a wide range of ordinary voltages.
Oh, okay.
So it is still very useful, and so the problem is it's so useful that it's easy to screw up and think of this as, I don't know, R defined as V over I. So yeah, V is IR, and it's all works perfectly.
Okay, so
not quite that easy.
So it's just that some materials are not ohmic and thus don't.
Right. Some materials and materials generally tend to be ohmic over some range of voltages. So it'll work for a while. If you did put 200 volts across this object, you probably would get 2 amps. But I'm not sure that if you put 1,000 volts across it, you'd get 10 amps, maybe. or 10,000 volts, you get 100. I don't know. At some point, it's going to stop working.
Okay, thank you.
Okay. And so, right, some materials have more resistance, some materials have less, right? There's a reason why, there's a reason why the light switch, if you have a small bathroom, I'll do a little architectural drawing of your bathroom, tub, toilet, sink. There you go. If this is a small bathroom, there's a reason the light switch isn't here. It's on the outside of the wall. So here's the door, and the light switch is wired. The switch is on the outside. If you've ever been in a little bathroom, the switch is usually on the outside. That is not so that one of your siblings can turn it off while you are in the bathroom. That's electrical code, because if your hands are wet, and there's a good chance they are if you're in the bathroom, your resistance, here you are in all your glorious stick figure beauty, something in the light switch, right? There's a line that's 110 volts above ground. And I know it's AC, but let's forget that for now. It doesn't matter for this. So there's a certain, right, human beings are kind of bags of water, some more than others. But your skin does have some resistance. So, if you poke something into you, you have very low resistance between, from inside your body through your bloodstream, because you're salt water. But there's a good amount of resistance on the surface of your skin. And so if you touch something that's 100 volts and your feet are here on the floor, there's still a fair amount of resistance between this surface and, the actual part of you that conducts, which is your blood and all the liquid in you. But if your hands are wet, then that has now all of a sudden your skin has much lower resistance. So this fixed amount of voltage will drive much more current if you have, if your hands are wet. And if you're if you're wearing boots, maybe you shower with your boots on. And so if you're wearing boots with rubber soles, they have a fair amount of resistance. And so your net resistance between your finger and the ground is higher. And so you'll get less current. And this detail of like, well, what about, this has a lot of resistance, but that has low. How do those all work together? That's what we'll talk about when we talk about actual circuits. Right? And this also answers, so questions so far? Plumbing, electrical work. Okay. So what was I going to say? Right. So if you have an electric, you have an electric wire. Yeah. So, your utility poles holding up an electric wire, right? This answers the age-old question of why birds can land on the wire. Beak. Hang on, let me finish my sketch here. Right, so why can the bird land on the wire? The bird can land on the wire because there is, right, the current is being driven down this wire that way. Somewhere there's a potential difference driving current through the wire. Incidentally, it's not because the wire is insulated. Insulation doesn't matter on high voltage wires. There's so much voltage on them that, in fact, so if you looked at the cross section of a wire, so if there's the conductor, it's fine. You could put an insulator on here around it. But if this is, 80,000 volts, it really doesn't matter, because if something touches this that's connected then to the ground, there's a huge voltage difference between this and this is the same if this is connected to ground, like if it's a wire or a person or whatever, and it's connected to ground, there's a huge voltage difference between there and there. A huge voltage difference means there's an extremely strong electric field. How do you get a big voltage difference between 2 points that are close to each other? You need a very strong electric field, because roughly speaking, electric field times this distance is the voltage difference. So if there's a huge voltage difference, there must be a huge electric field. and that huge electric field and voltage difference will drive current right through the insulator. So it really doesn't matter that the wires are insulated. Birds are just drones. Hang on, I have to catch up on chat. Okay. Good. So the reason the bird can land on the wire is there is some, since the current is flowing this way, there is some voltage difference between that spot and that spot. But the current, there's this piece, this little segment of wire between the 2 feet that has much lower resistance than the bird does. Primarily, not the bird's body, but the connection between the wire and the bird's foot. And so very little current flows through here. It would work for a person too. If you had enough vertical that you could stand here and see, now I'm drawing action stick figures. I've really, I've lost track of where we are. Okay. Right. So if you could jump from the ground and grab hold of the wires here and here, you'd be good. Please don't try these. Right? You'd also be fine. The problem is you can't get up there without climbing up the pole. And at some point, when you're touching both the pole and the wire, then there's a circuit from the high voltage of the wire to the 0 volts of the ground. And so then current will flow through you because you don't have huge amounts of resistance. And so you'll get current flowing through. All right. Birds aren't right. Birds are. Yeah, I know. I noticed that as I was drawing it, they have 2 extra knees. So, all right. My kids passed me in sketching skills sometime around age 4. My daughter always says, "Dad, you don't draw pictures in class, do you?" I have to. Okay.
What do you mean? Picasso here.
Yeah,
Beautiful.
It's a
the
different
composition. It's minimalist,
That's right. It's
new
minimalist.
style.
Right. It gets the basic meaning out. Okay. So mostly at this point, oh shoot, we're running out of time, which means we're not getting to play Name That Tune yet again, and we're going to miss another round on Tuesday. That damn test. Where are our priorities? Okay, one more thing we should quick talk about. Yeah, so what I'm hearing is Dan and I can put our forks in an outlet if we don't touch the ground. Yeah, don't do that. Although there was an electrician at our house because the other day because there was something I didn't want to rewire but needed rewiring, and electricians mostly work with live. They don't shut off the power when they work because they know what to touch and what not to touch. And so he was actually he was wearing boots and touching hot wire, live wire, but he was fine because he was insulated from the ground. Now, if he had accidentally reached out and touched the faucet, the faucet handle while he was touching a live wire with this hand, then I'd be calling 911. But I guess he does it enough that, so as soon as he touched the wire, that's at 110 volts. His finger is at 110. His body is at 110 relative to ground, but there's no circuit from him to ground. That's name that. Yeah, we can't play Name That Tune halfway through the test. Okay, so the last thing we're going to do is just quick in our last sort of 3 minutes, and this is just again, we talked about this before, but I want you to keep track of the difference between power and energy. Right? Energy has units of joules. Power has units of joules per second. They're not, I guess sort of they're related to each other. This also gets the name of watts. Right? Okay, so let's look for a second. What happens if let's say I have some resistor here and I'm flowing current through it? how much energy is being dissipated or used up here through this, let's say it's a light bulb. So I put a voltage V here, and we'll assume this is ohmic. So let's just say it's a resistor and it's heating up as current goes through it. And we'll talk more about that on next Thursday, I guess. So there's some current going through it, and that has some resistance R. And if we're going to assume this is an ohmic material, then we can use I actually, not V equals IV, V equals IR. I actually prefer to look at that as I equals V over R. It just makes more sense to me because the current is the result of a voltage across some resistor. Obviously, they're the same. So the question is, how fast are you using up energy if you do this? Well, what I know is so this is a subtle thing. There are I coulombs per second flowing in this circuit, and the voltage difference is V joules per coulomb. So think carefully about this one step. Every 1 coulomb that flows from here to here loses V joules of energy because it's V joules per coulomb. Right? So think about that again. Every one, since it's a V voltage, V joules per coulomb drop, that tells me how much energy the coulomb of charge loses when it goes from here, from the high side to the low side. So it's V joules per coulomb. And how much is going? Well, we're transferring a coulomb every second. So yes, I know you can see it by units, but I also want you to think about it in terms of common sense. Every coulomb that passes is dropping V joules, and I coulombs are passing per second. Then the power is the current times the voltage. The coulombs per second times the joules that each coulomb gives off when it crosses the circuit. So the power in watts is the current times the voltage, and it's joules per second. So you can just look and, we'll do this next class. You can look at some adapter and see that you can see how many amps of current it uses and what voltage it is. So like look at some USB adapter or something. It'll tell you the current and it'll tell you the voltage. The product of those is how many joules per second that thing is providing or producing.
I mean, if I may add, this kind of helped me understand it a little bit. I just kind of saw this. I mean, if you look at it, coulombs will cancel out and you'll give it joules per second just purely mathematically.
Yes. So that's what I was saying when I was saying, yeah, you can also just multiply the units and it works. But I think because these units, joules and power and voltage and current are so central to basically everything we do, I also want you, in addition to just multiplying the units, I want you to think about like physically coulombs per second flowing and every one of them losing or giving off V joules. And so it also should make common sense to you. In the same way that it makes common sense if someone's paying you $15 an hour and you work 4 hours, it's obviously $60. That just, it makes sense. I want you to be sure, yes, you can use units to do that, but make sure it also makes sense to you why it's that. Okay. All right. So I will, I'll see you guys I'll see you on Tuesday or in office hours. All right. And look at the online exam, but study first and then take the old exam as if it were a real exam, just as to get used to the.
Thank you, Professor. Have a great day.
Thank you. You too.